Welcome to Homework Lib.
Today we are going to be looking at the problem 42.31. This problem utilizes the equation 42.22 found on page 1422 of your textbook. This equation is laid out well by the authors with this graphic showing all the relative values with the note made by the authors as well as me that this E they give, these are two different E's, okay? This is the constant E associated with a natural logarithm. And this is the E up here, a fundamental charge, 1.6 times 10 to the minus 19, okay? Now, Boltzmann's constant here, we have a value for that in our book as well, 1.38 times 10 to the minus 23rd. I'm chopping off a few of the characters there. It's a little bit longer than that, but for our purposes, that's just fine. And then our temperature there is in Kelvin. Okay, now what we need to realize is that when you have a problem like this, we need to look at what data is given. All right, the first things that are given are forward bias voltage. So we have a voltage that's given, we have the current, and we have the temperature. Now, if we look at our expression that we found that's associated with a p-n junction, okay, we see that we have current, okay, voltage, and temperature, with everything else being a constant. What we do not have is saturation current. So if we can solve this problem for the saturation current, we can then just plug in the values in part A and B into our new expression. Okay, so my saturation current follows with this expression. I simply divided both sides by this part of the equation. Okay, let's go ahead and figure out what that is. So if I look at this, I have I saturation is equal to I 9.25 milliamps, okay, divided by the exponential of fundamental charge times voltage. Now, this is an important point here. My voltage I'm going to use, I'm not going to use millivolts. I'm going to convert this to volts. 0.015 volts. Okay, milli means 1 times 10 to the minus 3. Now, the reason I am doing this and not worrying about the milliamps up here is because in an exponential, we need to have dimensionless units in here. So what's going to happen is this has units of coulombs. Boltzmann's constant has mixed units of coulombs and Kelvin and volts, seconds. And we need to have this in volts just so our units work out. Okay, Boltzmann's constant, which we can look up in a textbook, 1.38 times 10 to the minus 1.38 times 10 to the minus 23, roughly. This is in Kelvin. Okay, and then minus 1 with our bar going this way. All right, if I evaluate this expression, I will get a value that is approximately 11.78 milliamps. Remember, just to avoid confusion, I left this in milliamps, that's fine, but in an exponential, we have to be dimensionally consistent, so we have to cancel all of our units out. So the units in Boltzmann's constant needed to have volts on the top. We can look at that perhaps another time. Okay, now that we have that down for part A, simply we can just plug these things straight into the expression using the proper voltages. Part A. Okay, so for part A, what we have is we want to know what happens in the system if instead of 15, if we have 10. Okay, well then that means that our voltage is going to be equal to 0.01 volts. Okay, and I'm going to plug that into my expression for I. I equals then my saturation current, 11.78, all right, times my exponential exp, we may have to move this bracket over, no problem. Okay, exp to the fundamental charge times 0.01 divided by Boltzmann's constant times 300. Okay, and minus 1. And I get a value of 5.55 milliamps. Okay. Now, when we do this problem, the next part of this problem, rather, part B, I'm going to put an input of V equals minus 0.015 and minus 0.01. Okay, as students, it is important for you to learn how to input these things properly into your calculator. Realize that, let's think about this. When I put in a negative value here, I'm going to have a negative expression for my exponent, all right, in the top part, all right? If I have a negative value up here, the whole expression after I evaluate the exponent is still going to be positive, okay? Let's keep that in mind, not make mistakes there. So let's call this IB1 and IB2. IB1 and IB2, where IB1 is associated with the first voltage, and IB2 is associated with the second voltage. And I get this, minus 5.18 milliamps and minus 3.78 milliamps. That's it, folks. Thanks for your time.